stiffness method, the first problem, I'll be walking you through each and every calculations so that you have the understanding and you have the confidence of this method. So you take 1 minute and bring all these three things: your notebook, your calculator, and your pen or pencil. You should be sitting with this, and I can ask anybody that you verify me this number now. So you should go and bring these things. You have 1 minute. Okay, so let's get started. Now, module 6, it is about analysis of kinematic indeterminate beams by using the stiffness method. Now, topics to be covered today will include introduction. So again, quickly we will go over the introduction of the stiffness method, prerequisites for using stiffness method, stepwise procedure of stiffness method for beam analysis, analysis of beam examples 1, 2, and 3, and then assignment. Now remember, today's lecture, the importance of this is that we will be going through certain steps which we will repeat for the analysis of the rigid joint frames as well as for the trusses also. So you need to be very careful while we are going through these steps. So now let's introduction. Now, why beams or why these structures are analyzed with the help of this stiffness method? The reasons are that it is systematic. You can find out the support reactions with the help of this method, and you can find out the internal member and actions also, which can be your axial forces, which can be your shear forces, which can be your bending moment. As we are discussing currently the beam, so beam element, it will be having only shear and bending moment. It will not have any axial action. If it has axial action, then we call it a beam column action, which is known as frame simply. Now, prerequisites again for this method, it's a repetition now. So you should be having enough concept of matrix algebra. You must know how to find out the kinematic indeterminacy. And you also be good at this using the formula for finding out the fixed end actions. If you don't know these fixed end actions formula, then you will have to go by the actual calculations by adopting some method, and it will take a lot of time. So you should be able to find out, especially for the normal cases. Now, stepwise procedure using stiffness method. Step number 1 will be that you will find out first the kinematic indeterminacy, and you will locate and label those locations which are now having the capability to move. So those now you will identify as redundant joint displacements. So this will be step number 1. And when you identify those as your redundant joint displacements, then corresponding to those you will also look for the externally applied actions, and those externally applied actions you will include them as AD matrix elements. So in step number 1, we are going to identify our unknown joint displacements, and then we will complete our AD matrix also. Step number 2, when we go, in this step, we apply the actual external loads on the basic kinematic determinant structure, which is our restraint structure. And we find actions at the locations of redundant joints. Already the redundant joints now in step number 1 we have identified and we have labeled them also, and we have assigned some direction also to that one. So that direction is our positive reference direction now. Now we find out the fixed end actions now corresponding to those now joint displacements. If they are coming in the direction of those joint displacements, we consider them as positive and we write its magnitude accordingly. And if it is in the opposite direction, we write this with the negative, and this will complete our ADL matrix. Now we will be writing the corresponding values to the unknown joint displacement. So it means the order of the ADL matrix will be same as order of the unknown joint displacements. Similarly, the order of the AD, the D's and the ADL matrix, all these three, the orders will be the same. Why? Because AD is corresponding to the unknown joint displacements, as well as ADL is also corresponding to the unknown joint displacements. So now we have completed AD matrix in step number 1 and ADL matrix in step number 2. Now two things are left in the equilibrium equation. One is the unknown joint displacement, so we cannot find it at this stage. And one is the stiffness coefficient matrix. So in step number 3, we will try to generate now the stiffness coefficient matrix. Now what we do to find out this stiffness coefficient matrix, we apply the redundant joint displacement on the basic kinematic determinant structure. And now to standardize this, what we do, instead of the actual displacement, we initially apply a unit displacement and then we multiply it by the actual one. So, and we apply this in the positive direction, and positive direction, again, it is coming from the step number 1, where we assume our unknown joint displacement. And this way we generate our stiffness coefficient matrix. So now we have all the 3 numbers. We have AD, we have ADL, and we have the stiffness S matrix also. So in step number 4, we go and solve the equilibrium equation now. And the equilibrium equation is AD is equal to ADL plus S times D. Already we discussed this derivation in detail, and the terms also, what the various terms are for. So if we rearrange this, D, which is the unknown, it is equal to S inverse times AD minus ADL. Once the unknown joint displacements are found, in step number 5, we go and we find out the member end actions. You can find out the support reactions, all the unknown quantities. So directly you can find them now with the help of these known joint displacements now. And once we know the member end actions, so in step number 6, then we draw the shear force and bending moment diagram. Now let's apply these steps to the actual problem now. So while looking at the screen, let me go and now it should be in the presentation mode now so that you can see it clearly. Okay, now with the help of, now it's taking a bit time, so okay, now you are looking at the screen now, so quickly you should be drawing this sketch now. A, B, C are the supports. At A, we have fixed support. At B, we have roller support. At C, also we have a roller support. Within AB, at the center, we have 30 kip load, and within BC span, we have a 20 kip, and it is also at the center, although it is not given, its location is not given, but you show it in the center, it is at the center. Now, AB, if you look at the location of this 30, it is 6 feet. At the bottom here, you can see it is given, it is called out here from A, it is at a distance 6 feet. Similarly, from C, you can give the same 6 feet, showing the 20 kip location. AB span is 12 feet and BC span is also 12 feet. EI is constant. Now, quickly you draw this on your sketch like you are sitting in your class and you are taking the notes now from the blackboard, and then we'll go and I'll walk you through each and every step now. And this will be the case, remember, only for problem number 1. For problem number 2 and 3, I'll be going very quickly over this. I will not be spending this much time. Now, take EI is equal to constant. We are not talking about anything about the cross-sectional area. It means the axial effects we are ignoring. So if we ignore the axial effects, first if we take the axial effects, if we find out the kinematic degree of indeterminacy or the degree of freedom of this problem, so A is not allowing any kind of, so here we have 0. At B, it is allowing horizontal translation and it is allowing rotation also. So 2 degrees from B we have, and similarly from C also we have 2 degrees. So this is total 4 degrees indeterminate problem. Now, if we ignore the axial effects, now 2 members we have, we need to now deduct these 2 members. So it is now and coming up with 2 degrees indeterminate problem. And what are those 2 degrees? That is rotation at B and that is rotation at C now. So theta B or theta C, will be giving it a general notation D1, D2, D3. So it will cover each and every translation and thetas and everything. So kinematic indeterminacy at the bottom in orange, now color you can see it is 2 degrees, and when it is 2 degrees, when we neglect the axial effects. So 2 redundant joint displacements should be chosen. Now it's your choice. If rotation at C you take D1 and rotation at B you take as D2. Somebody can say no, rotation at B is my D1 and this is D2. So you can switch these numbers. So this is your choice now. But remember, these 2 are your kinematic indeterminacy. Everybody shall be doing these 2 indeterminacy. Now, here now you can see this is the original structure now. This is our now location 1 at B and location 2 at C now. So the unknown now rotation at B I'm showing by D1, and the unknown rotation at C we are showing it by D2, and you can see its sense also these are clockwise. So clockwise rotation, initially I take this positive. Now this is again now your choice. You have the liberty. If you want to take it counterclockwise, you take it counterclockwise, but that will become your base direction then. Everything which will be coming in the counterclockwise, you consider that as positive then from this step onward. But here, clockwise rotation. So when clockwise rotation, so corresponding to this, clockwise moments will be also taken as positive. So step number 1, we are starting now. Selection of redundant joint displacements and assign coordinates at those locations. Also compute AD values. So now this D1 and D2, it is giving you now the base also for selecting the AD1 and AD2 values also. So D1 and D2 now you can see clearly clockwise. D1 is at B now rotation and D2 is at C the rotation. And here now clearly we write down their D1 and D2. These are our unknown target values now. So we will be finding D1 and D2. Now corresponding to D1, we don't have any moment now. So we put 0 value, no moment means no 0, and at C also you see corresponding to D2, again we don't have any external moment now applied, so this is also equal to 0. And problem 2 we will be taking now, if corresponding to D2 we have some moment, how we include it. Or here I can give you the example. Let's say at B a moment was applied in the counterclockwise direction, let's say 10 kip feet. So counter means it was opposite to this D1, so negative sign because of that opposite sign now, and minus 10 you include this here at the AD1 location. D2 we don't have anything, so that will still be 0. So now I hope you have noted down this sketch and all this 30 kip, 20 kip and those things. AD matrix is generated now, and step 2 we will be generating the ADL matrix. So first we need to make this structure as a restrained structure. Right now it is not restrained, at B it is not restrained, and at C it is not restrained. And what we will be restraining? We will be restraining rotation at B and rotation at C. So next slide now I am showing now the restrained structure now. A was already restrained, but B, what we restrained the rotation, and at C we restrained the rotation. And very simply, whenever you put a fixed support, so that is restraining each and everything, so that is becoming your basic kinematic structure, or your this restrained structure. So here you can see your restrained structure now, but make sure that we at B and C we are making these modifications now to the structure. Now, for the ADL matrix, now you see here, if I take you back to these steps now, so you should be comparing now this step 1 to the step 1 of flexibility method, and you don't get confused now. In flexibility method, instead of D's, we were having ARs as our unknown quantities. Right? The support reactions were, the redundant actions were the unknowns. Here the redundant displacements are unknown. Now corresponding to the AR, we were looking for the now giant displacements there. And to find out those giant displacements, if you remember, to find out the one was DRS matrix and one was DRL. So DRS matrix, it was now in place of these ADs now. We were looking for, is there any precondition now corresponding to the unknown redundant action? Here we are looking for the external actions now corresponding to the displaceable joints now. So DRS matrix was generated in the first step now, which were the displacement, the preconditions or the pre-displacements in the actual structure. Now step number 2 now, here we made, if you remember, we made the basic statically determined structure, which was known as release structure. And here now, this was a very laborious process now here in step number 2. Remember, in DRL matrix, we were using the conjugate beam method, or we were using the unit load method to find out the displacements due to the actual loads applied on the basic statical determinate structure. So you must be recalling that the conjugate beam method, making the conjugate beam method, and then loading it with the M or EI diagrams, then the resultant load, its centroids, and then if you are finding out the slope, we were finding out the shear in the conjugate beam, and if we were finding out the translation in the actual structure, the deflection in the actual structure, so we were taking moment at that particular section. So a lot of calculations were involved there. Here what we need to do now, here corresponding to the unknown giant displacements, we will be just finding out the corresponding actions now. And those actions from where you will be now for the 6, 7 simple cases, you will be remembering those member end actions. When you load a fixed ended beam, what kind of actions and how much actions are generated. So step number 2 now, we are going now quickly, and then I'll be giving you 1 minute to record all these numbers. So restraint structures acted upon by actual structure. Where the release structure was acted upon by the actual loads, here the restraint structure is acted upon by the actual loads, and compute the values of actions in the restraint structure corresponding to the redundant locations. This will generate ADL matrix and fixed the fixed end actions. Now, the basic kinematic determinant structure was at A, we were originally having the fixed support, so we are not doing any now changes to this A support. At B was a roller support, so we now converted this to a fixed support. And at C also we were having a roller support, so we now converted this one also as a fixed support. So this was our basic determinant structure. At the center of AB, we were having a pointed load, and the center of BC also we were having a pointed load now. L are the lengths, and P1 and P2. This is a general case we are discussing, and our specific case it is giving at the bottom of the screen now. P1 was 30, P2 was 20, L was 12, and this L was also 12 now. If we have fixed ended beam, pointed load at the center, L is the span, so the member end actions now, the moments will be P1L divided by 8 and P1L divided by 8. Or simply if we talk about the general case, so this will be PL divided by 8 now. As the moments are balancing each other, so half of this load will go to A support and half of this load will go to B support. So that is why here we see P1 divided by 2 and P1 divided by 2. If we have unbalanced moment, so you will have to distribute that accordingly now by inducing a couple there so that the unbalanced moment can be balanced. Now, for the right one, again, we are using this PL divided by 8 now. Now, this is becoming your general case now. If you have a load at the center of a fixed ended beam, the moments at the ends generated will be PL divided by 8, and its vertical reaction will be P divided by 2 now. This is for the pointed load. If the point load is off center, let's from the A support, it is at distance A, small a now I'm saying, and from the B support, it is at a distance small b now. Then there we use an equation PAB square divided by L square. This will be the moment at A now, MA. PAB square divided by L square. You can now go and check this in some structure book. And MB will be equal to PBA square divided by L square. And then the reaction you can find out due to unbalanced moment and then distribution of this load also to the support. So with the help of those, you can add them up algebraically, and whatever values you get there, those will become your reactions. Now applying this now, this was for the pointed load now we discussed. Now if you have a UDL now, and let's this UDL is applied throughout the span. So for that case, the bending moment now produced at each end will be equal to, let's W is the intensity of the load, so it will be WL square divided by 12. And the vertical reaction produced at each support will be equal to WL divided by 2. So that is another general case now. Similarly, now you can find out for the triangular load, if a couple is applied, and already we discussed that in module 5, those general cases. Now let's apply this now to this general condition at the bottom. Now we are specific to our this problem now. 30 was for the AB span. So 30 means now you should take out your calculators and now verify these values. So PL will become 30 multiplied by 12 and divided by 8 now. So I am running my numbers, you should be running your numbers. So 30 multiplied by 12 and divided by 8, and 45 I got. And exactly 45 we are showing these movements, 45 and 45. Vertical reaction, so half of this 30, it is 15 and 15. Similarly for the BC span now, so P is becoming 20, L is again 12 yeah, and divided by 8 now, so 30. So here you see 30 and here also we see 30. So all these values are verified. So quickly now you don't need to draw this top one sketch. You have to be specific now because we don't have that much time. So quickly you draw these diagram, or you can draw at the B support if you want to show one joint. So that is fine too. For this side you show 45 clockwise, and for this side 30 feet you show counterclockwise. That's it. Again, in the box, you can see 1 and you can see 2. So those are the unknown giant displacements, those locations. And from this diagram, we will be completing now our ADL values. Now, with this sketch, you write down clearly that from here, we will be now completing our ADL matrix. For completion of ADL matrix, and remember second values which we will be needing, so we will be completing our AML matrix also from here when we go to the stage of the member and actions or support reactions. Even you can complete from this sketch now. So that is why we are writing all the member and actions, because let's assume the vertical reaction I want to find out, VA I want to find out with the help of which will become my AM1 now. So AM1, let's say it is the support reaction at A in the actual structure. So my AML1 will become this 15 now. This will become my AML1 value. So this sketch will be helping you in completion of the ADL matrix as well as AML matrix. So clearly if you have a red pen now also, so write down in a note that from here you will be now picking your values and you will be completing your ADL matrix and AML matrix also. With this much explanation, you got the time also to write down this sketch and numbers. So let's move to the other one now slide. Before moving there now, let's decide about the ADL1 matrix. And right now, I cannot fix like which one values I'll be including because it will depend on your time availability now. You may not go in such a detail now. So later on, you will decide which one member actions you want to find out with the help of the stiffness method. So right now, we focus on our ADL matrix. So ADL1 will be coming from the moments here. Why? Because moments are corresponding to the rotation. Why we are taking rotation? Because rotation at B was unknown. That was our D1. So now if you see MBA, which is clockwise, this 45 magnitude. So this is in the direction of the D1. So we take this plus 45. But here MB, which is again corresponding to the D1, which is counterclockwise, so we take this minus 30 now. So 45 minus 30, which is 15. That is the value of ADL1 matrix. We are not taking 15. These are also corresponding to this one location. But remember that rotation was our unknown. It was not the deflection. Right? It was not the deflection or settlement here, or translation, vertical translation. If vertical translation was unknown here initially, then we include this 15 and 10 which are the vertical reactions. So those are the corresponding actions then. But in this case, plus 45 minus 30, this is our ADL1 value. And ADL2 value coming to the 2 location. Now, if you see 30, it is in the clockwise direction. Clockwise was the direction of D2, so it means plus 30. This is our ADL2 value. So that easily you can generate your ADL1 and ADL2. So next slide, if you see here, ADL1 is equal to 45 minus 30, 15, and ADL2 is equal to plus 30. So ADL1 and ADL2, 15 and 30. You know, already the explanation of ADL1 and ADL2 you have at the bottom already. We discussed this when we were developing these this equilibrium equation. So you clearly now write down ADL is equal to, this matrix is equal to 15 and 30. You should be putting this with whatever sign you get here. In this case, we are getting both positive. So, and you see here at ADL1 where D1 was involved, there the contribution of two members were coming. One was BA member, one was BC. So here you can see now the contribution of these two member and actions now. One was positive and one was negative. So you should not be having any problem now when you go to the next problems in generation of the AD matrix as well as ADL matrix also. Now stiffness method, the stiffness now matrix we will generate. So in stiffness matrix now, this is parallel to the when we were generating the flexibility coefficient matrix in the flexibility method. There we were applying the unit action we were applying corresponding to the redundant action. And here we will be applying a unit displacement corresponding to the displaceable joint, which is our degree of freedom. So here now the basic kinematic determinant structure or restraint structure is acted upon by a unit value of displacement. And computation of stiffness coefficient matrix S values in the basic kinematic determinant structure corresponding to the redundant joint displacement locations. So what we do now, our problem is now 2 degrees indeterminate problem. So we will be applying now a turn by turn now displacement. So first we apply corresponding to D1, and remember, when we are applying to corresponding to D1, so we will release now the joint displacement at that particular location, and the other locations will be still clamped. They will be still restrained. It will not be allowing any kind of rotation or displacement. And similarly, then we go to the second position. We allow displacement at the second location, and we clamp it at the first location. So here now in orange line, you can see these instructions. Now, when we apply now at the first location, your elements of the first column of the stiffness coefficient matrix will be generated, which will be S11 and S21. The last subscript now you can see it is due to 1 now. At 1 we are releasing the displacement. So at 1 due to 1 and at 2 due to 2. And when we allow rotation or displacement at the second location, so then the second subscript will become now accordingly 2 now. So S at 1 due to 2 and 2 due to 2 now. And now let's show this now how we do it for this specific problem. Now, step number 1 of this 3 will be, we are allowing now rotation. Here you see at 1 now, which is support B. This yellow line, we are rotating it to this inclined red line by an amount theta is equal to 1, because rotation was unknown. So we are giving a unit rotation there. And because of this rotation, how much member and actions will be generated? Already we discussed that at the near end, the moment generated will be in the same direction as that of rotation, and it will be 4EI theta divided by L. At the far end, it will shift by half of the amount. So thus it will make 2EI theta divided by L. Now it will cause unbalanced moment now in that particular span. So we need to balance that by a balancing couple. So that is how these vertical reactions are generated at the ends now. 6EI theta divided by L square, 6EI theta divided by L square. Similarly, for the BC span, you can use the same concept and you can develop these member and actions. Now, this was the general case now at 1. How now fixed support we cannot rotate. So what we do initially, we provide a hinge support here so that we allow this rotation. So you can, if you want to show here, you can show a hinge also, but this kind of rotation is also okay. At the bottom sketch now, what we do, we apply now our own condition now. Remember here, if you see, we don't show any actual loading because here we want to show just now the unit displacement corresponding to the D1. So that is why we have a basic determinant structure. And corresponding to D1, we are allowing now rotation, unit rotation. And as a result, now we are finding out the member end actions. Now, if you see here, 4EI theta divided by L, let's start from the AB span now. So my near span for the AB now, it is B now. Why at B we have this rotation activity? So 4EI theta is 1 now. So 1 we don't want to put here because if we multiply this again, it will be the same thing. So 4EI times 1 divided by L. L is 12. This AB span 12, 1. So 4EI 12 at the far end, it is 2EI half of this one, and 6EI divided by L square will become 6EI divided by this 12 square. Again, you should be very clear about this direction. Why this movement is clockwise? Because rotation given was clockwise. Far end the same direction, half of magnitude. So the unbalanced couple produced now, it is in clockwise direction. So the balancing couple should be in the counterclockwise direction. And we got these numbers also. Now coming to the BC span now. In BC span, again, rotation here at the B. So this is our near end. So the moment produced here will be 4EI divided by 12. Again, you see here this curve is this curved head, it is in the clockwise direction showing the rotation. It's again the direction of this rotation. This 12, remember 4EI divided by 12, which is L, it is from the BC span. Now this corresponding span you will have to include. Far end now, which is C now, 2EI divided by L, half of the MB. And again, the balancing couple now, if you see the unbalanced moment is in the clockwise direction. So the balancing moment will be in the counterclockwise direction. And that is how we get 6EI divided by 12 square. Again, this 12 is this BC span. So now with this one, you clearly write down that you will be picking your first column of the stiffness matrix from here. You will be generating. This sketch will be helping you. And when you get to the stage of member end action, so AMD, the first column of the AMD matrix, you will be generating from this one. So if you have a right pen, now red pen again, you should be making these two comments here with this sketch. You should draw this bottom sketch, clearly now show you these member end actions. And write with this that this will be used for generating of the first column of the stiffness coefficient matrix and first column of the AMD matrix. You take 1 minute now and complete this sketch. Now, your S11 will be coming from the member end actions which are corresponding to D1 now. So which one are those member end actions? One is this MBA, which is 4EI divided by L. From BA span this moment, which is 4EI divided by 12. And from BC, again, we have clockwise 4EI divided by 12. So algebraic sum of these two now will give you S11. This way you can complete your S11 coefficient value. So it will be 4 divided by 12 plus 4 divided by 12 EI, which will be 8 O EI over 12. This will become your S11 value. S21 value will be corresponding to D2 now, a 2 due to 1. So it is again clockwise positive sign, and it will be 2 EI divided by 12. So this will complete the first column of the stiffness coefficient matrix. Here, corresponding to D1, you will be looking for the member and actions, which are moments. One is this 4EI divided by 12, one is this 4EI divided by 12, both are in positive direction, clockwise direction. So you simply add them up, and for S21, it will become 2EI divided by 12. Now, if you are looking for the AMD values, let's the reaction, as we said, vertical reaction at this one, we took the positive, AM1 was in the upward direction. So AMD first value, it will simply become minus 6EI divided by 12 square. Why minus? Because it is opposite to that AM1 direction. So AMD similarly share to the left, if you include that as a member and action, so you will be picking this value. Shear to the right of this beam, you will be picking this value for the AMD matrix, and shear at C if you include, so 6EI. Moments if you include, so you will be looking for those corresponding moments here. So that way you will complete the AMD matrix also. So let's focus now on the stiffness coefficient matrix. So here now you see in the next slide, if we move, this is now your S11. As I said, from two members we are getting the contribution. 4 EI over 12 was from each one, so we end up with 8 EI divided by 12, and S21 2 EI divided by 12. So this is, and this is the explanation of what is S11 and S21. Now second column we will have to generate now. So for second column corresponding to D2 now, we will be giving now the rotation, unit rotation. So to show that position now, here now you see what we are doing here corresponding to D2. So here you can see D2 is equal to 1 we are putting, and D1 is equal to 0 we are putting. So here we put this fixed support, and at 2, if you see this yellow line, we are rotating it to this inclined red line by giving it a unit rotation now. C is becoming our near end now, so 4 EI theta divided by L, and the same clockwise direction this moment is generated. Far end, which is our end B now, so again you see here 2 EI theta, half of this amount, the same clockwise direction, and this is the balancing couple now. Now fixed support, so if we are not showing these now rotations and these vertical reactions, the moments and the vertical, it means those quantities are 0 now here in this manner. Now to apply this to our actual now problem, so here now 4 EI theta is 1 now divided by L, L is this 12 feet, so 4 EI divided by 12. To the far end 2 EI divided by 12, and balancing couple 6 EI divided by 12 square and 6 EI divided by 12 square. Now looking for the corresponding value. Now with this sketch you write again with the clear, with the red pen now clearly that second column of the stiffness coefficient matrix and second column of the AMD matrix will be generated from this sketch now. We'll be referring to this one to generate the second columns of stiffness coefficient matrix and the AMD matrix. Now coming to now S1 to S at 1 due to this 2 rotation now. So if you see here, BA is not doing anything, not contributing. We have only this 2 EI divided by 12 now. So 2 EI divided by 12 plus 0. You see here again clockwise. So our S12 now becomes 2 EI divided by 12, and it must be equal to 2, which we generated in the previous one. That was 2 EI divided by 12. This one is 2 EI divided by 12. So once you get the confidence, then you don't need to repeat this. Once you find S21, you should be good at this S12. You don't need to find this one. But this is just to, initially you don't have the confidence. You now find them separately and then you match them. If they are matching, it's fine. If they are not matching, so there is some mistake now in the calculations. S2 due to 2, which will be S22, it is over 4EI divided by 12 now, which you will pick from here. Why? Because this is the corresponding action to the D2. So this way we generate S12 and S22 now. So quickly you draw this now. For this specific case, you draw this bottom sketch and then we go to the next slide now. And there we complete our stiffness coefficient matrix. We write it very clearly there. Okay, so now let's see now S12, you see here it is 2EI divided by 12, so it is final now 2EI divided by 12. And this one should be S22 actually, so let me make this correction now. So this is now S22, which is 4EI divided by 12. This one, and this is final now, so we make this S22, so 4EI divided by 12. And with this now, you can write very now clearly that what is your stiffness matrix. So you are here now, you see this was your S1, this was S21, this was S11, this was S21, this was S12, and this is S22 now. So here we complete this one. You don't need to go through all these explanations when you are solving a problem. Because of the time constraints. So stiffness matrix now you write at a location now very clearly. Step number 1, we found the AD matrix, and that was coupled, remember, by with the labeling of the D's, unknown joint displacements. Those D's are becoming our reference, actually the baseline. And then in step number 2, we found the ADL matrix. And step 3, we found the stiffness coefficient matrix. Now in step 4, now we are in a position to apply the equilibrium equation. So let's go to the equilibrium equation now. This is now the equilibrium equation. And finally, what we have these unknown joint displacements is equal to S inverse times AD minus ADL now. So what we will be doing now, here we will put our stiffness coefficient matrix. And AD values we have in this particular case, AD1, AD2, both were 0 because we were not having any external actions corresponding to the displaceable joints. ADL we found, so we can write the ADL1 and ADL2 value also with their specific sign. So here now, this is the basic equation in the matrix form. And here now we put the values now. Here now, if you see, it was 8 EI over 12, 2 EI over 12. This was 2 EI over 12, this was 4 EI over 12. Now, what we did now, EI over 12, we took common, and when we took the inverse of that, so that become 12 over EI now. And still we have within this bracket the inverse sign, so you will have to do all this operation to find out this inverse. And as I said, AD1 and AD2 were 0, 0, so we put those value. ADL1, if you remember 15, from where we found this 15, it was 45 minus 30, that number 15. ADL3, it was 30, so we put this value, we solve this simultaneous equations, and D1 is coming equal to 0 and D2 is coming minus 90. Minus 90 means that the initially which we assume clockwise rotation at support C, it was wrong. It should be counterclockwise. But anyways, remember for onward calculations, we will be using this D1 and D2 with these specific signs now. These signs are fixed now, so 0 and minus 90 will be used. Now remember, sometimes now the examiner can ask you, looking at the paper complexity and all these things, that you just find out, you give me the rotation at B and C now. So your problem is solved now. You don't need to go through now rest of the calculations, finding out the member indexes and all these things. You have solved the problems. So you should be careful readers also. You should be specific to the whatever is asked. Otherwise, if you do for extra, go for extra calculations, and if it is your first problem, let's say, you will lose time. You will not be having enough time for rest of the problems then, so you will lose marks also. So always now you have to read carefully what instructions are given there. Remember, sometimes the examiner now, he can ask you that you take, let's say, a rotation at C as D1 and rotation at B as D2. So you will have to take those rotations accordingly now. You don't have now the liberty to go, and at B you should be taking one, and at C you should be taking as 2 now. So always read the instructions very carefully. Now, step number 5 now, the member inductions. That is our normal step now, and we did the same way in the flexibility method also. Here, instead of the member inductions, I'm interested in finding out the support reactions now, so you can find out because all the informations you have. So what is the basic equation now? The basic equation was AM is equal to AML plus AMD times D now. So instead of the member now, what I'm including now, S. Instead of M, I'm including S. S is showing the support reaction now actually. So this is the only change now in the journal format. Now, AS1 is where you should be looking at the reference now. At support B, the vertical reaction, we are showing with AS1. The vertical reaction at C, we are showing with AS2, and the vertical reaction AS3 now. And you should be looking at their positive directions also. All we consider in the upward direction as positive. So again, it is your choice now, which one, downward you want to take positive or upward. So from here now, you are setting a reference now, and we say the upward direction we take positive. And this will become our equation. AS is equal to ASL plus ASD times D now. So quickly you draw now this reference also, so that we can refer to these specific values now. Okay, so now how to now complete this ASL matrix and ASD matrix? D already we found it was, but remember in D here this EI is missing, so EI is still there. It is 0, and this is minus 90 divided by EI. So you show it by 1 over EI times 0, and this ones are, I can show it here also. Let me 1, and it is divided by EI. So it's there now. I go this AS1, and here now AS1. So you made a note of this one. Now let's how we complete ASL and ASD matrix. So already I told you that the basic, now this kinematic determinant structure under the actual load from where we generated the ADL matrix, from there we will be completing our AML matrix also, or ASL matrix also. So here, this was the location of AS1 now. So ASL1 will be corresponding to the same location now. And the corresponding actions, which are the vertical reaction, this 15 and 10, both are in the upward direction. So 15 plus 10, this 25, this will become your ASL1 value. ASL2, it is corresponding to AS2 now, and we will be looking for the vertical reaction at this location, which is 10 kip. So here we include this 10 kip. Similarly, ASL3, which is corresponding to AS3 now, 15 kip upward direction, so 15 kip. Here we include. So this way we complete now. Now remember, when you come to the member and actions, you don't need to redraw this one. Already you clearly wrote these values in step number 2 there. So you will be going back there, referring back there, and you will be picking your values from there. So ASL1, ASL2, and ASL3. Now, one explanation, you were interested in the member and action, and the member and action was just the shear to the left of this support B. So just to the left of this support B, now we have 15. So you will have to take 15 then, because this is just to the left of this B. If it was shear just to the right of this B, then that 10 is corresponding to that one. So you will take 10 at that location. Then here we are taking total reaction. So that is why we are adding this 15 and 10. And this is how we get this 25. So quickly now you draw this bottom sketch and you complete your ASL matrix. Next, we will be completing now ASD matrix, and that will be coming from where we completed our stiffness matrix. Okay, I hope you have completed this slide. Now we next go to the ASD matrix. So first apply a unit rotation at redundant location 1, and then add 2 in the restraint structure as shown below. So this is at B location, we provided this theta is equal to 1 now, and these member and actions were generated. So now I'm not going in this detail now. But ASD11, which is corresponding to AS1, you need to add up now these reactions now. 6EI over 12 square, 6EI over 12 square. From the left, we have 6EI over 12 square upward direction. So this is our positive, and this is 6EI over 12 square down. This is negative. Algebraic sum of these. So it is becoming 0 now. Plus 6EI over 12 square minus 6EI over 12 square. Coming to ASD21, which is corresponding to AS2 now, we have plus 6EI over 12 square. And ASD31, it is 6EI, so minus 6EI over 12 square. This is minus 6EI over 12 square. So 0, 6EI over 12 square minus 6EI over 12 square. This will complete the first column of the ASD matrix. To complete the second column, we give rotation corresponding to theta 2 now. So unit rotation corresponding to T2. Already we generated this, if you remember, for generating the second column of the stiffness matrix. The corresponding values now we will be looking. So ASD at 1 due to 2 now, it is minus 6EI over 12 square. SD22, it is plus 6EI over 12 square. And SD32, it is 0 now. So we complete this one, and here you see all these values. You can verify now these values, these values. So I hope it will be fine instead of the L square. So they have the actual now. numbers in decimals. I think it is coming 0.0417, and this is also minus 0.0417. ASL matrix is complete, ASD matrix is complete, D already we have, so you can find out these support reactions. So here we put these values, and these are now coming your support reactions. AS1, which was the vertical reaction at B, now it is coming plus 28.75. So here you see. At AS2, it is 6.246. So here it is 6.246. And at AS3, it is coming 15. If it was with negative sign, so we just reverse this direction. So we now put the values of these support reactions found on this sketch. Now with this much information, you are in a position now to find out the member inductions and draw the member shear force and bending moment diagrams. But now to show you, want to go in more detail now with the help of the stiffness method, and you identify now these one now, that these are now your interest you want to find out with the help of this method. So AM is equal to AML plus AMD times D. Let's the shear at this AM1, AM2, AM3, AM4, AM5, AM6, AM7. Remember again that already if you found this AM1, this was AS3 now, so already you have this value which was 15K. So what you are going to get? You are going to get again the same value 15. So what is the purpose of doing it again? No. But this is just to show you how can you find out these. If you are finding the member inductions, you can find it by this method. Similarly, AM2 and AM3, if you add them up, these member and shears, it will become your support reaction at B now. We found the support reaction here, it was 28 point something ordered. So we don't know how much was from the left side, how much was the shear from the right side. So if you want to spread them, it's okay, you can go by this method. AM4 already we found this number, it was 6 point something or whatever, you can confirm this. The directions now, again, upward and clockwise movements we are taking positive. So AM5, which is the movement in the clockwise direction, we are assuming at support A. Let's support B now. If once you found AM6, so AM7 is already found, but only it will be in the opposite direction of that AM6 now. So you don't need to find them separately if you don't have time. It is understood that they will be balancing each other. So you make a note of these locations and these labeling now. In corresponding values, we will be picking now for the AML and AMD to complete these matrices. Look quickly, if you want to make, you will be getting these slides now, it will be uploaded. So you just write down AM1 here, you just write down 2, 3, 4, you don't need to write again and again AMs and AMs. So this is how you quickly make your notes now. And you show their clockwise directions also. Now, going to the next slide now. Here now, AML values, how from where we will be picking. So again, from where we generated the your ADL matrix. Our ADL matrix was generated. The strand structure under the actual loads from those member inductions now. So AML1, these are corresponding now to those AM values now. AML1 corresponding to AM1, AML2 corresponding to AM2 now, and their actual values are given here now. So AML1 will become plus 50, AML2, if you see, again plus 50, AML3 plus 10, AML4 plus this 10, AML5, it is minus 45 now because it is opposite to the direction of AM2 or AML5, AM5 or AML5. So 45 if, and it is counterclockwise here, opposite to that one, so it is minus 45. AML6 plus 45 and AML7, again, if you see the signs are not matching, so this is minus 13. This way you complete the AML matrix. Why we didn't include this? You could have included this AML8 also, but by observation it was a roller support there, so whatever operation you do, finally you will get zero movement there. So just by observation you can see it is zero. So why we are going to do all these hectic calculations? By observation, that is understood that that is equal to zero. You can verify those by including this by AML8 and AM8 now at this location, and eventually you will end up with zero. So here now you see 15, 15, 10, 10 minus 45 plus 45 and minus 30. So we have completed this AML matrix. AMD first column now, it will come from here, from where we generated first column of the stiffness coefficient matrix. Here you see theta is applied at B. So AMD 1, 1, 2, 1, 3, 1, you can see all these. And what was the base for this? For this, the base was the AM selection. Here now, AMD 1, 1 is coming minus 6 EI over 12 square. Upward was positive, but this is downward, so 6 EI over 12 square. Again, you don't need to draw this again. Already we did this for the generation of the stiffness coefficient matrix. AMD 2, 1 will become 6 EI over 12 square. AMD 3, 1 minus 6 EI over 12 square. AMD 4, 1 6 EI over 12 square. AMD 5, 1 2 EI over 12. AMD 6, 1 will become 4 EI over 12. Then AMD 7, 1 will become 4 EI over 12. So first column of the AMD matrix is complete now. Similarly, now to generate the second column of the AMD matrix, we refer to this one from where we generated the second column of the stiffness coefficient matrix. Here you see now again the base for these now labeling is the from where we did the AM. AMD 1, 2, if you see now we have 0. AMD 2, 2, here we have 0. AMD 3, 2, we have minus 6 EI over 12 square. AMD 4, 2, 6 EI over 12 square. AMD 5, 1, we have 0. AMD 6, 2, we have 0. AMD 7, 2, we have 2 EI over 12. So second column of the AMD matrix is generated. So I gave you, already you have these values, so I don't want to give you more time now to redraw this sketch, and you don't need to. So this way now you see here, we now again in decimals form, we have, you need to verify all these values. If you want to verify one value, let's verify this last one. This was 7.2, which is 0.167, it will give a problem. So let's go there and verify this. What is 2 divided by 12 now? This 2 divided by 12 is coming. So how much is 2 divided by 12? Let me verify. 2 divided by 12 is equal to, it is the same value, 0.1667. So it is written here. Now rest is now the matrix operation. Now this is now the matrix form. We put the values here, and after plugging in the values, going through the matrix algebra, you get all these member inductions now. And accordingly, we put them on the sketch now. You see here, AM1 is 15, so 15 in the upward direction. AM2, 15, so just to the left, 15. At the AM2 location, we have 13.72. At the AM3 location, we have then AM4, so 6 point, and exactly now you can see this was our AS315 kip, and this was AS2. Exactly, we have the same numbers, and if you add them up, 28.75, again we have the same reaction from these values also. AM5, it is minus 45. Our assumed direction was clockwise, so we reversed the direction because of this negative, and we put this on the sketch now. this AM6, which was the movement just to the left of this B, so 45. So we put this in the same clockwise direction, but to the right of this B, it is becoming minus. So instead of clockwise, what we do, we put this in the counterclockwise now, balancing each other now here. So you got again the verification as I said. So now with this much information, you plug now, if you put the actual loads also here, which was 30 kip and which is 20 kip here, very easily by looking at the loading and these reactions, you can draw your shear force and bending moment diagram, which are shown now on this. You don't need to do any further calculations now. Everything is here now. So you can complete your shear force diagram and you can complete your bending moment diagram also. And with this, we complete our problem. Now, you can turn on your mics and you can start asking me questions now. You refer me to the slide if you have any confusion, if you need any clarification, so let me know. I'm available to answer your questions. Now, let me tell you one thing, that nowadays, most of the time, communication, it is done by this virtual method. Somebody will be calling you from the site now, he will be on the phone and he will ask you that you go to this number drawing and tell me that what we are doing here, or let's say if can we make these changes, or we have problem at this location. So you need to understand this virtual language now. This is need of the time now, and especially in such kind of a situation where we have this social distancing problem. So you should be used to these things now. Hope you have verified each and every number now. So, yeah.
Sir.
Yeah.
सर ये स्टेप नंबर 2 में जो है सर स्टेप नंबर 2 में सर ये अगर हमारे पास रोटेशन और डिस्प्लेसमेंट दोनों हो तो फिर एडीआई की वैल्यू फिर किस तरह फाइंड करेंगे?
अच्छा, वो किस तरह फाइंड करेंगे? वी आर गोइंग टू डिस्कस दिस इन प्रॉब्लम नंबर 2 नाउ. Problem number 3 are also coming, right? So we will be discussing specific to this one now. You need to be limited to this problem now, where we are involving only rotation. तो अगर यहाँ पे अगर कोई question है आप पूछ लें. अब अगर settlement या deflection आ रहा है वो कैसे हम करेंगे? So in the next now 2 problems we will be discussing those situations. And if you don't understand those ones, so at the end of the lecture you can ask me questions then.
Okay.
I'll give you another section. Okay.
सर ये स्टेप नंबर 3 में जो साइन हम लेते हैं, हमारे पास जो हम रोटेशन जो लेते हैं यूनिट रोटेशन, उसमें हमारे पास जो एक साइड में हमारे पास डाउनवर्ड वो रिएक्शन आता है सर, वो अगर एक्सप्लेन करें.
अच्छा, स्टेप नंबर स्लाइड का पता है आपको कौन सी स्लाइड की आप बात कर रहे हैं?
स्लाइड नहीं सर, स्टेप नंबर 3 है.
अच्छा, स्टेप नंबर 3 में मैं चला गया. दिस इज स्टेप नंबर 3 नाउ पार्ट 1, जहां पे हम 1 पे हम प्रोवाइड कर रहे हैं. ठीक है, तो कौन सा आपको नजर आ रहा है आपको?
यस सर, नजर आ रहा है.
अच्छा, तो कहाँ पे आपका ये 1 लोकेशन है ना आपका, तो किस साइड की आप बात कर रहे हैं?
यस सर, ये जो राइट में है, राइट साइड में जो हमारे पास
ये वाला.
यस सर, ये वाला हमारे पास डाउनवर्ड क्यों होता है?
अच्छा, ये क्यों होता है ये देखिए. पहले तो ये मूवमेंट्स की तरफ आप जाएंगे ना, मेंबर एंड एक्शंस, आप मूवमेंट आप जनरेट करेंगे. अब क्लॉकवाइज और क्लॉकवाइज कैसे आ रहा है ये आपको पता है कि नहीं? यहाँ पे भी आपको कंफ्यूजन है.
क्लॉकवाइज ठीक है सर, मूवमेंट सही है.
अच्छा, ये ठीक है. तो अनबैलेंस्ड मूवमेंट आपका क्या है? क्लॉकवाइज में आ रहा है ना.
यस सर,
क्लॉकवाइज. अगर अब इसको क्लॉकवाइज मूवमेंट को आपने बैलेंस करना है, ठीक है, तो उसका तरीका क्या है कि आप कपल प्रोवाइड करेंगे अपोजिट डायरेक्शन में, ताकि आपका ये क्लॉकवाइज आपका बैलेंस हो. अब कपल का डायरेक्शन क्या होगा? अगर ये आपका क्लॉकवाइज आ रहा है तो कपल आप बैलेंसिंग कपल आप काउंटर क्लॉकवाइज में आप प्रोवाइड करेंगे. तो अब नीचे और ऊपर वाला आपको समझ आ गया कि नहीं? अब ज्यादा एक्सप्लेन कर लूं अब इसको?
यस सर, समझ आ गया सर. ओके सर.
अच्छा, ठीक है. और ये लेफ्ट वाले के लिए भी यही कंसेप्ट हम यूज कर रहे हैं. देखें, ये क्लॉकवाइज आ रहा था आपका अनबैलेंस मोड, तो उसको बैलेंस करने के लिए हमने बैलेंसिंग कपल जो है ना वो काउंटर क्लॉकवाइज में हमने सबको प्रोवाइड कर दिया। क्योंकि अगर आप इसको ऊपर करते हैं और इसको आप नीचे करते हैं ना तो फिर क्या, ये तो उसी डायरेक्शन में, अब तो ये तो और भी अनबैलेंस्ड कर लेगा इसको। क्लियर?
क्लियर सर।
अच्छा, ओके, नाउ एनी अदर क्वेश्चन? Okay, so if you don't have any other questions, so it is now 9:26 now. So till 9:45, now let's have a break now. And after the break, we are going to continue with problem number 2 and problem number 3. Now utilize, if you want to utilize these 20 minutes also for let's review and these things, you go quickly over these one. Problem number 2 and 3, now I'll be running quickly over those one because we need to wind up all those 2 problems with the available 1 hour then. And also, you know about your midterm also, it will be in the week of 22nd of June now, so you should start preparing those things also. So let's meet now at 9:45 now, okay, for the remaining class.